Hello, Math 10B students. I'm going to go over a worked example from section 3.7, which is improper integrals. And this is number 347 in our textbook, the Strang book. And it says the integral from 2 to 4 of dx over x minus 3 squared. And so the whole thing with improper integrals is that they're improper because we're taking an integral over some kind of asymptote. And so there are two types of improper integrals. One of them that sort of announces itself to you. It says there's an infinity in one or both of the limits of integration. And those cases, it tells you that you're taking an integral over an infinitely long domain. So you're taking a horizontal asymptote, right? So it goes forever and ever in a horizontal direction. The other type of integral of improper integrals are this type where there's a vertical asymptote. And so the fact that it's improper is sort of hidden inside the notation. You can't see it, you have to be on the lookout for it. So we got to be a little like a little detective. And so we can tell here that this function 1 over x minus 3 squared has a vertical asymptote at x equals 3, and that number x equals 3 is in between 2 and 4. And so we can't just use the fundamental theorem of calculus, which tells us that we have to have a continuous function or at least a nicely behaved function. So we have to split it up where that asymptote happens and then treat those cases the way we do, the same as essentially idea of the way we do with the improper integrals of the other type where there's a horizontal asymptote. And so, you know, even if you don't know what the picture of the function looks like, you can still do this process. But at 1 over x minus 3 squared, it's just 1 over x squared, which is like our volcano function, but shifted over by 3, right? So we have, you always have to think about which way it's going, right? So this one gets shifted to the right by 3. So this is 1, 2, 3. And instead of like 1 over x squared, we have a vertical asymptote at 0. So now this has a vertical asymptote at 3. And the function, you know, without being too careful about it, looks vaguely like this. It's not very well drawn because it should be symmetrical about that x equals 3 line. And so when we're trying to compute the integral from 2 to 4, right, essentially what we're saying is we want to know what's the area under the graph of the function, right, between the graph and the x-axis for this whole region here, right? And so at the outset, one might say, oh, hey, it's just infinitely, there's just an infinite amount of area because it goes up forever and ever and ever and ever. But actually, sometimes it converges to a finite area. We have to check to find out. And we don't have any way of computing an integral that goes up, that has this infinite asymptote in the middle of it. The fundamental theorem of calculus does not work. And so by definition, what we do is we split this up into the integral from 2 to 3, right? And we use 3 because that's where this asymptote is happening. So the integral from 2 to 3 of 1 over x minus 3 squared dx plus the integral from 3 to 4 of 1 over x minus 3 squared dx. And that's still not enough because we still can't use our fundamental theorem of calculus. We have to take a limit. And so the idea here is that we pick some t value like here, and we're like, okay, well, I can't compute the infinite integral, but I can compute the integral from this t point up to where it hits the graph, and then I can compute that area, and that's a finite area. And then we're going to let that t get closer and closer and closer to 3. So we'll take the limit as t goes to 3, in this case from the left side, and then compute the limit of those areas. And that's what our integral is going to be equal to. So I'm going to compute these things one piece at a time, because by definition, if one of them diverges, then the whole integral just automatically diverges by definition. So we'll just do one at a time. When you're doing this at home, you can try to read ahead. So it looks like, if it looks like one side is going to diverge and the other's not, then you try to do the diverge side first so that you can be done and not have to do as much work. Here, it's symmetrical, it's the same thing. So we'll just do one at a time. If it converges, then we'll compute the other half. If it diverges, then we're done and we don't have to compute the other half. So we're going to start by just computing this integral from 2 to 3 of 1 over x minus 3 squared dx. And this, again, just like in our picture here, we can't compute this thing going all the way up to 3 because of the vertical asymptote. So instead, we have to compute the limit as some variable. You can call it whatever you want. I'm going to call it t. Oh, not going to infinity. I take that back. T is going to 3. We have to indicate from which side. So in this case, we're coming in from the left side, which is the side that's like sort of on the negative side, even though all the numbers are positive. So it's the side that's less than 3. So that's what this little minus sign in the superscript means, is that we're coming in from numbers that are less than 3. And then we're going to compute the integral from 2 to t of 1 over x minus 3 squared dx. And because that t value is some other number that's not 3, it's coming in from this side. Everything is nicely well defined, so we can compute this finite area and then take the limit as t goes to 3. On your Friday assessments, if you don't write this down with this limit notation, I promise you, you're not going to get credit ever. So just don't even bother, right? Make sure you understand what this notation means. Make sure you know how to use it. Make sure you do use it on your Friday assessments. We want you to get credit. We want you to know this notation. It's like the heart of the whole problem. So even if you do everything else correctly and you get the correct answer, but you don't write this notation down, you're not going to get credit. So please, 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 please save yourself some time and effort. Write down this notation. It's the most important part of the problem. That said, you still have to finish it. Okay, so we're going to compute this limit as t goes to 3 from the left side. And now we have to compute this integral just like we would any other integral. So this is like a 1 over u squared, right? So if you want, you can go off and compute it on the side. So we're like the integral of 1 over x minus 3 squared dx. Which you can rewrite as the integral of x minus 3 to the minus 2 dx. Since it's just an x with the derivative of just 1, we don't really have to do a u substitution. We're taking the integral, so we're going to add 1 and divide. So this is equal to minus 1 over x minus 3, right? Or x minus 3 to the minus 1, so it goes to the denominator. And over here in the general integral, we would add a plus c. Over here, we're going to use the fundamental theorem of calculus, so we don't have to worry about the plus c. So this is our integral. So now we're taking the limit as t goes to 3 from the left-hand side of this 1 over antiderivative x minus 3, evaluated from 2 to t. This is the limit as t goes to 3 from the left-hand side of minus 1 over t minus 3 minus, which is plus 1 over 2 minus 3, which again is minus 1. T is going to 3, but this is in the denominator. So the limit as t goes to 3, the numerator is fixed, the denominator is going to 0. So this is blowing up to infinity. We can even tell which side, right? T is coming to 3 from the left side. So we're plugging in numbers like 2.9, 2.999, right? So they're numbers that are less than 3. We subtract 3 from it, we get a negative number. We're multiplying by a negative, it's going to positive infinity. Actually, we can see that from the picture as well, right? So this part is going to infinity, and therefore this thing diverges. And so the whole integral 2 to 4 dx over x minus 3 squared also diverges by definition. So that's how we handle this kind of problem.